what is a pattern? I mean, nothing is out of the blues for you guys, right? So let's start discussion and discussing that. Okay, so this is how we are going to start with organic chemistry, right? Now, whenever you have got any new topic starting here, it will be always bifurcated into these subtopics. So you'll be always starting with the nomenclature and the classification part. What is that functional group? How it is going to be classified into various terms? What are the various ways of classification? First, these things are to be always talked about. Very elementary thing, but still again in J, in NEET, one or two questions do pop up from these trivial concepts only. So they are just marks, kind of like marks for the taking. But if you be if you become complacent, then it is going to be trouble for you. So we'll be covering this a little. Nomenclature I won't be covering for this particular chapter, or for that matter other chapters also, because nomenclature for all the chapters will be studied together in one particular segment, and you can look for various videos on nomenclature already there in your app, right? So we'll be discussing about methods of preparation. There will be some general methods, there will be some specific methods of preparation, right? And this is also very important. Both general and specific methods of preparation is very important for us, because a lot of conversions that come in questions, they do have their base on these particular methods, right? And remember that what preparation of one particular group of compounds will be treated as reactions, chemical properties of another class of compounds. So there is always a very close link between these type of preparations and chemical properties. So if you pay attention to them, then overall preparation will be not that vast, because a lot of things will be shortened, right? Acha. Then in physical properties, it is very important to focus on the anomalies. Most of the classes of compounds will have got quite similar physical properties. The trends will be quite similar, right? So if you start learning the trends, what is a pattern, like classification, periodic classification for elements in periodic table, the trends that you learn there, that more by various groups do have got similar trends. So that is applicable here also. You need to understand the anomalies also. This is because this is where your JEE and NEET exams they do focus on the anomalies, which is not very straightforward, right? Then in chemical properties, we need to focus mostly on the attacking reagents, the byproducts, the intermediates, right? And also the new properties that are being obtained by conversions from compound A to compound B, right? And all this will culminate and lead to the interesting learning of various mechanisms, some twists and turns. All this come together will come together and give you a very beautiful picture of organic chemistry. Organic chemistry, mind you, just like physics, a lot of thing depends on how good you are in visualization. Like in physics, you have got free body diagrams. The better you are with them, easier it is for you to solve the problems. Here also, your imaginative imaginative quotient is actually going to help you out in solving various problems and have a better grasping, right? So with this, let us quickly start into the next segment, bacho. Okay, so what we have here, haloalkanes and haloarenes. See, all these are basically derivatives of alkanes. We can say they are the derivatives of alkanes. and normally we represent alkanes as Rx. Sorry. Yes. Normally we represent the alkanes as RH, right? Now if you take this hydrogen out and substitute this with some sort of functional group, then it belongs to a new class of compounds. So in this chapter, since we are focusing on alkyl halides, so we'll replace this H by some halogen atom X, right? So now we have got this new representation as Rx, that is your alkyl halide as the common name, or haloalkanes as the IUPAC name. Same goes for your aromatic system also, right? So in aromatic system, that is systems containing benzene, C6H6, right? So it has got 6 hydrogens. We are just highlighting one hydrogen here. Now replace this hydrogen again by some halogen atom, right? And what are we going to obtain? We are going to again obtain here benzene is there, all right, but now this hydrogen is replaced by S. So this becomes our aryl halides or halo benzenes, right? Achha, so this is what we have also written here. So I hope this part is very much clear to you guys. Now let us talk about the in daily life, what are the applications we have got. I mean, it's not that it is only confined to the labs, because ultimately after doing a lot of research in lab, we do get them to use in our daily life also, right? Like CCl4 is a very good solvent, right? It is used as a solvent, and of course it's a volatile liquid. Then you have got these chloroquine tablets, right? Chloroform to, I mean, since childhood we have all of us watched so many movies, and in movies whenever the bad guys, the goons, they have to, you know, make somebody unconscious, सिर्फ दिमाग में chloroform आता है, but chloroform, mind you, is not, it does not work as swiftly as is shown in serials or movies, right? Hollywood or Bollywood, doesn't matter, right? And also chloramphenicol is a very well known eye drop solution. All these are common things of daily life. They do have got this, see, they do have got use of these halogen part in the alkylated form or in the aryl form, in the aromatic structure also, right? Okay, now it's not that everything is very good about haloalkanes, means because whenever the compounds are there, then it totally depends on what kind of uses you are making. It may be beneficial for you, for the environment, or it may turn out to be quite harmful or dangerous for the environment. Nowadays we are already suffering so much with your environmental crisis also, right? So like I'm in Delhi, and in Delhi the pollution factor is a big thing. Other than corona, globally we are also under tremendous pressure because of this pollution, right? It is always in the severe zone. So lockdown has also not helped much. So all this, and also when these CFCs, that is chlorofluorocarbons, they get released in atmosphere because of various human actions, like in fridge we used to have CFCs first as a coolant. Now it has been banned across the globe, knowing its devastating effect on our atmosphere. So all these CFCs, suppose in like small factories are releasing these CFCs. Our residential homes, because of the fridges and other ACs, they are releasing these CFCs, right? Like chlorofluorocarbons and all. So when they go up in atmosphere, they interact with sunlight more intensely over there, they break up, right? And they do release these halogens like chlorines and all, who further break ozone into oxygen. Now ozone hole was created because of these things only. Now that's why it is banned globally, and it has recaptured it. It has again healed itself quite nicely. It is much better than what it used to be, like a decade or two back. But still, tomorrow again we invent something and we start using these kind of compounds, which again harm us further, other than the pollutions that we are facing. So these are the negative sides of these compounds, right? Acha, now we are going to discuss about classification part. There are few ways in which we can classify. First of all, we should know how or why are we doing this classification, right? So why do we classify? So classification is very important because it becomes very easy for us to learn. Okay, if I can classify a compound in say category A, then a certain pattern evolves. Then it becomes easier for us to identify them, recognize them, and learn about their properties. The same way your S block, D block, P block, F block in the periodic table helps. Here also it is of the same understanding, right? Acha. And what are the various classifications we generally divide this groups into? First, we talk about nature of CX bond, right? Then, of course, degree of the carbon attached, that is primary, secondary, tertiary, right? Hybridization, carbon can have only 3 hybridizations. So what are the various hybridizations of carbon with which the halogen is attached? So it is that classification. Number of halogens, of course, right? There is only one halogen, two halogen, three, or many halogens like mono, di, tri, and so on. And of course the nature of halogen, right? It is more electronegative, less electronegative, what is the electronegativity difference? All these things do matter. Okay, now first we are talking on the basis of nature of CX bond. Now we know that your carbon and the halogen, it is partially positive and this is partially negative. So that means this is a polar bond, right? There is a polar bond. Now this carbon also may have different hybridizations in different environments, right? So whenever it is bonded to an alkyl group, wherever it is bonded to an alkyl group, let me check if somebody is asking a question, because I am going to get them in the WhatsApp. Okay, I'll if you have got any doubts or anything you would like to ask in between, please go ahead and do so, right, in the segment that is given over there. Now, since it is not being displayed over here, so I'll be taking help of my colleague who are going to pass on the doubts to me, right? Acha. So you can see that normally when we deal with alkyl halides, alloalkanes, what we have got, as we discussed to start with, normally your alkane is what? CnH2n plus 2, right? So what we are doing, we are taking one hydrogen out, so it is becoming CnH2n plus 1, and then you have got the X over there. So this is what is belonging to this class, right? Then you have got aryl halide. Now when we say aryl halide, that means this chlorine is bounded with an aromatic system defined hydrocarbon, right? Aromatic system means something which satisfies your Huckel's rule, and there are few more parameters which you might have studied under general organic chemistry, right? Acha, like sp2 hybridized, cyclic resonance, right? All these things are there. So benzene is a very good example for that. So that's why they come under the category of aryl halides. So all these carbons are sp2 hybridized. Here also you can see that this is non benzenoid aromatic system. You can see that oxygen has got like 2 lone pairs, so 2 of them it can participate over here. So it is also satisfying your Huckel's rule, and hence this is also sp2 hybridized, right? So it is also an aromatic system. Acha. Now one is pure aliphatic one. You can have alicyclic one also. You have got aryl part also, and then you can have mixture of both, right? So mixture of both means your halogen will be present on the side chains. So here you have got them on the side chains here, right? Now this carbon attached directly to the benzene ring is called benzylic carbon, right? And these benzylic carbons are very activated ones. They do drive a reaction in a particular direction, which we'll explore and learn in coming topics, right? This is how it is presented. Now very important to know these terms over here. If 2 hydrogens are there on this benzylic carbon, then it is your benzyl. If 1 hydrogen is left, then it is benzyl, like benzaldehyde also. And if all the hydrogens are gone, then it is benzo, right? And you also know that if you are removing 1 hydrogen from here, so this bond is available, like here it was this bond is available for a new halogen, then right now from benzene we don't get benzyl. Benzyl is different. You have seen that this is benzyl. This is what? This is phenyl, right? So C6H5 is phenyl, right? Okay, so classification continues, and now we also have got this special vinylic halide and allylic halide. So basically what is vinylic halide? Whenever your halogen is directly attached to this double bond. Now you will say that here also we had in the aryl system the halogen was directly attached to an sp2 hybridized carbon. So what is the difference between aryl halide and vinylic halide? The difference is that there is an isolated double bond. This is bonded to sp2 hybridized, but it is an isolated one. It's not part of the aromatic system. It is either aliphatic or alicyclic in nature. So this is aliphatic in nature, right? This is alicyclic in nature. For example, if I draw it like this, right? So this is like but2ene, and if I put my halogen say over here, so I put a bromine over here, right? So this is an aliphatic system. Since it is, this bromine is present on a double bond, so it is a vinylic halide. So this belongs to the category of vinylic halide, right? I hope this part is clear. Now allylic halides. So the position just after the double bond, which is sp3, this position as well as this position just after the double bond is sp3 one right now, and this is called your allylic position, or allyl, any halogen attached over there will be called allylic halide. So right, this is a good example of allylic halide. In the alicyclic form also, you see, so you have placed the halogen after the double bond, so it is sp3. This carbon is sp3 hybridized. Same goes for this carbon. This is also sp3 hybridized. So if I place like one, say iodine over here, right? So now you have got, in this particular example, you have got both bromine as your vinylic halide and iodine as your allylic halide. So I hope both vinylic and your allylic positions are clear to you. Also remember that, you know, taking out this vinylic halide is very difficult compared to allylic halide. This position is more active, more reactive in comparison to this position. Why is it so? We'll explore after some time, right? In this chapter only. Okay, now based on the type of degree associated with the carbon atom. So what is the logic here? any carbon to which the halogen is attached, if it is attached with only one carbon, and does not matter how many carbons the other carbon is attached with, but this carbon is attached with only one carbon, then it belongs to the class of primary, right? So it is a primary carbon atom, and hence this halogen belongs to this primary halide category. Similarly, if this carbon is attached to two carbons, then it is secondary, and if three, it is tertiary, right? So primary halide, secondary halide, and tertiary halide, right? Acha. Now, based on this understanding, if I ask you one question, I'll give you C5, or let me give you, yes, C5H12. Draw its isomers. Draw isomers of this such that and you have to draw, say we have done chlorination, so one chlorine is to be put here by replacing one hydrogen, right? And you can have various isomers of this compound. So you have to identify those structures of the alkanes, of the isomers, right? You have to identify those structures which will give you 4 different isomers. 4 different isomers of monochloride. Suppose I am treating them with chlorine, right? So you have to tell me which isomer of C5H12 will give us 4 chloroalkane, 4 different chloroalkanes, different 4 isomers. The isomer that will give you only one monochloride, and the isomer that will give you 3 isomers of monochloride, right? So from this simple understanding only we can have such kind of a question. So you have got C5H12. So what should be the approach in these type of questions, right? Basically, draw the isomers of C5H12, and you know that key with C5H12 you might have studied in class 11, must have studied in hydrocarbons. So you can have 3 different isomers. One is this, one is 2-methyl butane, and third one is 2,2-dimethyl propane, right? So these are the 3 possibilities of C5H12. Now let us see, if we put halogens here, what are we going to get? We have to have one chlorine only, not more than one chlorine only. So if you put one chlorine here, you replace one hydrogen by a chlorine, you can have this position. You can have the second position also, like this will be 1 chloropentane, this will be 2 chloropentane, this will become 3 chloropentane, and then you have got repeats, right? So if you put it here, then this becomes 2 chloropentane, 1 chloropentane. So we won't get into these 2 positions. So what we see? We see that 3 different monochlorides can be obtained. See, if you see carefully, third question is asking you the isomer that will give you 3 monochlorides. So 3 is that means what isomer? This is N-pentane. So which isomer of C5H12 will satisfy third? Is your N-pentane. So this is for third option. Now let's check this out. I've got this one, right? You can have chlorine here also. Now see, this position is exact replica of the first position, so this is a repeat. We can exclude this. So you have got this one and this one. So you can see that there are 4 different positions where you can have chlorine, and all of them will be a new isomer, right? So this is your first option, right? It has asked about that isomer of C5H12 which can give you 4 different isomers of monochlorides. And the third one, doesn't matter. See, in the central carbon you cannot have anything because its tetravalency is already satisfied. So you have got these 4 different methyl groups here, right, as a terminal carbons, but all of them are identical. So that means if you put in any one of them, then other 3 are simply repeat. So you can have, whatever you do, you can have only one monochloride isomer of this. I mean, one monochloroalkane from this. So therefore this is for the second one. So I hope this is very trivial but still very important to get hang of these type of questions also, to have for a better understanding, right? So let's move on. Okay, now we talk on the basis of hybridization, right? So we can have carbon in with 3 hybridizations only: sp3, sp2 and sp, right? So sp3, all your alkyl halides, benzyl, allyl, everything has got, that is this one. This is sp3x, right? This is what we have got. sp2, so aryl halides, vinyl halides, that means your carbon has got a double bond. One bond is paired here and the other one has got halogen over here. So this is sp2. Next is your sp. Of course it has to be triple bonded as it is shown over here, right? So these are the various classifications based on the hybridization. This is very important when we do conversions. We learn about chemical properties and your preparations also. So these classifications is very important at that point of time. Okay, based on number of halogen atoms, right? So as we discussed in the problem just few moments back, I was stressing on the fact monohalide. So that means if the whole alkane system has got only one halogen, right, then that is your monohalide. 2 dihalides, tri, tetra, you can have poly also, more than 4 also, right? In the aromatic system also we can do the same classifications: mono, di, tri, tetra and so on, right? Acha. But this dihalide has got few other classifications. It can be done little differently, and that's why we are talking about the dihalide one specially, because again in various reactions and preparations it does have got an important role. Kaise? If you have got both the halogens on the same carbon, right, you can have, but it is also terminal, and if it is inside somewhere, then it becomes non-terminal, right? So terminal, non-terminal, but both of them are geminal. They are also called geminal. Geminal means on the same carbon. They are all on the same carbon. Now if they are on the adjacent carbons, then they are vicinal, right? See, vicinal. Both of them are, and here it is geminal, right? Acha. And isolated when they are at least one carbon away, and they can be further apart, right? So that is when they are isolated dihalides. Remember, geminal and vicinal, they will play important role, and hence I wanted to discuss in dihalides also you have got these classifications which are definitely very helpful to us while doing various questions, conversions and other things, right? Acha. Now on the basis of nature of halogen atom, what do we have? We have got 4 different halogens. So whether it is fluoroalkane, chloroalkane, bromoalkane, and so on, right? So RF, RCl, RBr, and Ri. We are going to focus mainly on RCl and RBr, to some extent on Ri. We will by and large avoid RF. We won't get much into it because it's very quite a risky affair to make fluoroalkanes. You need to be very extra cautious. So mostly we'll be focusing on chloroalkanes and bromoalkanes, and sometimes on iodoalkanes also, right? Okay. Nomenclature, as I discussed, it will be done separately. For various classes of compounds, a common platform for nomenclature is there, right? And it will be discussed in the common video over there. You can already, few videos are there in the app. You can check it out over there, right? So no need to discuss over there. I presume that you guys have got fair enough idea of nomenclature. We'll proceed accordingly, right? So very important segment now, preparation of alkyl halides. Very important segment. Okay. Acha, before we get into it, normally what happens that, you have got few types of reactions, right? Like substitution reaction. This you must have studied in class 11, types of reaction. Substitution reactions, right? Then you have got elimination reactions. You have got addition reactions. And you also have got rearrangement reactions. These are the types of reactions. Especially we learn about them because they help us in understanding why a certain mechanism is there through which you are obtaining a certain product, right? A certain class of compound you are getting with the help of these various big categories of reactions. Now see, substitution means you are replacing one atom by another atom, or one atom by some other group of atoms, something like that. One group of atom by another group of atoms. So this method, substitution, you can replace something by a halogen, and hence you can very well use substitution as one of the methods for preparation of alkyl halides, right? What about elimination? Can we use that also? Now think about it. Elimination means to remove something, to extract something. If you extract something, how come you are getting alkyl halide? So if it is already present in the system, why to remove it in the first case, right? So basically elimination is not we are looking for while learning preparation of alkyl halide. So that is how you can across various chapters you can have these 4 headings in your thought process, and then you can make it simple and learn accordingly which categories I am going to look for. So you have to do less of rote memorization and more of logical thinking you can put into it, right? Addition reaction, of course you are bringing something new from outside. So by bringing something new from outside, we can introduce halogen atoms, right, and make alkyl halides. So this is definitely going to work. Rearrangement, of course, is more about moving an atom from one place to another. So if it is already an alkyl halide, so like you have already got a primary alkyl halide, you are making a secondary alkyl halide, but still it is part of alkyl halide. So this is also something we are not looking for right now, but it may play a role. Remember that it may play a role. So right out of these 4, elimination is not we are going to look into. So we are going to start with substitution as our modus operandi to start with, and the first one comes for us for today is alcohols. We are going to prepare alkyl halides from alcohols, right? That is your ROH, right? ROH. So basically if you are able to somehow remove OH with the help of a halogenating reagent, that is a compound or a chemical that can provide you halogens, right? Then X can replace OH, substitute OH, and then you can have RX over here. These reagents are basically your attacking reagents. These are your attacking reagents. And here alcohol can be taken as the substrate, right? So these attacking reagents are generally of three types. You must have studied in GOC. One, they are called nucleophiles. Then you have got electrophiles, right? And you can also take free radicals as the attacking reagents. Right now, X here acts as nucleophile because it has got a negative charge, it has got high electron density, and it is going to replace OH. While going, it is going to take its own electron, so OH minus will become, and it is also a nucleophile. So a nucleophile can replace another nucleophile, right? So we'll talk about all these things also in future. So here basically we are dealing with an attacking reagent which is nucleophilic in nature, right? Which is nucleophilic in nature. So right now we are going to focus on this type of attacking reagents. These are all halogenating attacking reagents, and mainly we are going to deal with your halogen acids, phosphorus halides, both trihalides and pentachloride actually, and thionyl chloride, right? So HX, then PX3 and PCl5, and third is your very important agent thionyl chloride, that is SOCl2, right? So before going further, I'll just check if there are any doubts from your side. Okay, so I have not received any. Please don't shy away. If you have got any doubts, feel free, ask them, right? Acha. Now, so we are starting with your halogen acids, HX. So you can see that it's kind of a displacement, or you can say double displacement reaction. So you have got alcohol, ROH. You are reacting this with the halo acid, HX. So R is going with X, H is going with OH, right? So you have got RX, you have got HOH here. Fine. Now, the very important property that you have to keep in mind is that there is a certain order. There is a certain order of these halo acids. We know that in case of halogens, electronegativity decreases down the group, but size increases down the group. Hence, acidic behavior, acidic property increases substantially down the group. So HF is the weakest acid, halo acid, while HI is the strongest acid, right? You can see that is in accordance with the bond length. Longer the HX bond, weaker it will be. So as I told you that down the group from fluorine to iodine, size is increasing substantially. Larger the size, more difficult it is for hydrogen's 1s orbital to overlap with the p orbital, the corresponding p orbital of the halogen, right? So with fluorine, 1s and 2p can have better overlap. With 3p it is little lesser. 4p of bromine further less. With 5p of iodine it is least, right? And hence can be easily broken. And as per valence bond theory, we know that more the overlap, stronger the bond. Here the case is opposite. Lesser the overlap, weaker the bond, and better the acid, right? Acha. So that's why Hi is strongest and Hf is weakest, and its weak property, the weak property of Hf you have already studied last year in ionic equilibrium. Hf is one of the weak acids of which many questions were there, right? So this is what we have got here with halogen acids, straightforward, replace them. But then there are certain conditions under which it can be done, right? So generally what do? We either pass the dry gas, these halogens, the dry gas that we got, dry HCl, dry HBr, through a solution, right, where they can react with the alcohol. Or what we can do, we can, in place of taking the gaseous stuff, we can have the concentrated acidic solutions and heat them with alcohol. So either way this can be done from the practical point of view, right? Acha. And as far as HBr is concerned, we always use the 48% HBr, right? So these are the two methods generally with which we can use HX in while preparing your RX, right? Okay, now if you want to introduce bromine, there is another method for for HCl we have got for chloroalkanes we have got the previous method, but for bromine also we can use the HBr stuff, Hi stuff also. But then we have got different methods for both bromides and iodides. So if you take sodium bromide, right, if you take sodium bromide and react with this alcohol in presence of sulfuric acid, so basically what is going to happen is that sodium bromide and these two will together form sodium bisulfate, sodium hydrogen sulfate, right? And this bromine will then replace OH, which will combine with one hydrogen from the sulfuric acid, and of course water is going to be formed, right? Okay, so acha, in presence of we generally do not use Hi for this with H2SO4. Can you tell me why we avoid using any iodide like Ki or NaI with H2SO4? Why? Because H2SO4 is a very strong oxidizing agent also, right? So basically your I minus will ultimately get oxidized to I2, right? So that's why you see when it is about iodides, we are not using H2SO4, rather we are using phosphoric acid, right? Potassium and OH, again displacement reaction is going on, but in absence of sulfuric acid, right? So yields are pretty good. You can see that with the help of 95% phosphoric acid, either like as I told you, just mentioned, you can have sodium iodide or you can have potassium iodide also, but we are not going to use H2SO4. It is there in your NCERT in text question also, right? Why H2SO4 is not used? So you can see that Ki is simply oxidized to I2. Once it is oxidized like this, then the whole reaction is destroyed. So output is not going to be the amount is never going to be the same the way we want it, right? So very poor yield will be there, so we avoid it. Okay, now comes your Groove's method, right? What happens in Groove's method? We use zinc chloride. Now zinc chloride here is used as a catalyst. So in presence of zinc chloride, your this, see, RO, this is basically your carbon oxygen bond. This bond is weakened, right? And the more it is made weak, will be easier for OH to leave the system, and hence it will be easier for X to enter. Got it? So basically what we are going to have here, ROH when reacts with HX in presence of zinc chloride, it is easier for us now to form RX. But there is a certain order for alcohols here. Tertiary alcohols react fastest, primary reacts slowest, and in that also methanol is the least reactive, right? So this is for tertiary alcohols. All you need to do is simply take that in a test tube in a beaker, and you can simply, you know, shake it, warm it a little, and reaction will be there. But for primary, you do have to warm it for like 15-20 minutes continuously to obtain the final product, right? It takes time, right? Okay. Okay. SN1, SN2 will discuss further, right? See, I told you that this is a nucleophile that is attacking. This is a nucleophile, right? So a nucleophile is participating in a substitution reaction. Hence, all these reactions are basically your SN reactions. That is, there is a short form of nucleophilic substitution reactions. Now, you must have already studied chemical kinetics. So it is either first order or second order. So whenever primary is involved, it involves always the always your second order. Primary always goes through second order, while tertiary always prefers first order. There are few nuances of having the first order, second order in terms of SN1 and SN2 that we'll discuss later, right? During the chemical properties, we'll discuss that in great detail. All the stereochemical aspects, their enantioscopic aspects, stereoselectivity, everything we'll discuss over there. And that is a very interesting topic, right? Okay. Then comes your this is your groups method. Basically, how it is, what is the mechanism behind this groups method? We are discussing it here. We have just simply wrote that, you know, ZnCl to HCl there, ROH, yani alcohol is there. So Cl is going to replace it. But what happens behind it? This is what we are learning here. So see, oxygen is acting here as a nucleophile. Zinc, with zinc, it is going to attach its pair of electron, right? So what is going to happen? Let me quickly check. Okay. Fine. So it is going to attach itself with zinc. Of course, then it is going to lose its electron density. So you have got a positive charge over here, right? Now, what should happen? Yes, separation, right? So it is going to pull its pair of electrons and release R plus. So this is gone. R plus is released, and what is going to happen now? Yes, your halide will, that is your X minus, will come and get attached with R plus, right? Will come and get attached with R plus. So I'll move further. Okay. I'll pause for 2 minutes. I'll just pause for 2 minutes. Yeah, I guess I'm back live. I'll just confirm once. Okay, so now let us try to understand what is this Lucas test that helps us in distinguishing various alcohols, primary, secondary and tertiary. You will study this in the alcohols chapter also, but since we are already preparing alkyl halides from the alcohols, so let's talk about it. Basically what happens, and the reagent that we used here in Groove's method is your Lucas reagent only. So what we do in lab, Lucas reagent is obtained from, you can see that it is obtained by dissolving 32 grams of zinc chloride in 20 milliliter of concentrated HCl, right? So you take a beaker, you have got 20 ml of HCl which is concentrated, right? And to this you add 32 grams of ZnCl2, right? So what we do, I mean from this solution, once it is prepared, we take like we have to make totally 10 ml, so 8 ml of this and 2 ml of the alcohol. It can be primary, secondary and tertiary, right? So what happens when you add this 8 and 2 ml, that means your Lucas agent plus alcohol, right? Primary, secondary or tertiary, you can have either of these three. So if it is tertiary, then it is immediate turbidity. What is turbidity? Cloudiness. You will see the whole I mean in your test tube, the whole thing seems to be quite cloudy here throughout. Why? Because your alkyl halide is forming, tertiary alkyl halide is forming, and it is not properly soluble. It is not properly soluble in your water. Aqueous solution is there, or alcohol is also there. So it is not properly soluble and hence it is turbid in nature. If it is secondary, then it takes time. It takes approximately 5 minutes, right? And for primary, it takes a lot of time. So you can say that even like for 15-20 minutes, half an hour, you will see that nothing is happening. So that is clearly primary. So this is a very, very good test to identify what type of alcohol you are dealing with. So it is kind of a distinguishing test, right? Okay. Now next we come to the best method, as I talked about, Darzan's method. It is known as Darzan's method. Why is it the best method? I am referring time and again, because when you treat alcohols with thionyl chloride, you get gaseous sulfur dioxide, so it escapes. HCl is also gaseous, it will also escape. What you are left with? You are left with pure alkyl chloride, which needs no further purifications, right? And hence we get best preparation method with the help of this. But we cannot have thionyl bromide or thionyl iodide. Why? Thionyl iodide does not exist simply, and it is very unstable, so expecting it to give us alkyl bromides is futile, right? So we rely more on thionyl chloride, and we do get very good results, excellent results with thionyl chloride and preparation of RCl, right? Acha. Now what is the background, what is the mechanism of this, right? Let me check if there is any doubt. Okay, so see, we have seen the main reaction, but basically what is happening here? When you are treating alcohols with thionyl chloride, so there is one chlorine exchange. You can see that there is one chlorine exchange with OH and Cl2. So one chlorine is gone, one is retained, so you get this stuff. So when this HCl, because this is you are using the pyridine, using pyridine as solvent, so when you are having HCl with pyridine, pyridine is going to take up hydrogen and you will be given chloride, but hydrogen is removed and you have got your Cl minus. Now this Cl minus is going to attack R and leave this out. It is going to attack R via SN2 mechanism, which we'll learn later, and this will leave out this will form sulfur dioxide, right? This will form sulfur dioxide. This Cl will extract hydrogen from here and form HCl and go away, and all you will be left with are Cl. So this is a very good method of preparation of your RCl, right? Okay, now we talk with phosphorus halides, right? When you do it with phosphorus halides, if you balance it, see, 3 moles of halogens can be given, hence 3 moles of ROH is needed. So stoichiometrically your 3 RX will be formed, and of course 3 OH is released, which will go with phosphorus, forming phosphorus acid. But this is applicable only with chlorine and bromine, right? And if you use pentahalide, only PCl5 can be used, because PBr5 and PI5 does not exist. PBr5 is highly unstable, so PCl5 will still work, right? One chlorine is transferred here, and the chlorine is used up by hydrogen, and then you have got POCl3, right? Acha. But if you want to have good results of PBr3 and PI3, then you have to use it with red phosphorus, because then it will be formed in situ. In situ means during the reaction only it will be formed, and the similar reaction will be taking place over here. So this is a good method for both bromides and iodides, right? Acha. Okay, now the question is, in case of alcohols, in case of aliphatic alcohols, simply treating them with HX or SOCl2 or phosphorus halides helped us in forming the corresponding your alkyl halide. But we try to do the same thing with phenol, for that matter, then such results are not obtained, right? Like if I treat phenol with say HCl directly, nothing is going to happen. You treat this with HBr, nothing is going to happen, right? So why these cannot be easily removed? Why these why the OH on an aromatic system cannot be easily removed? So you can say that your nucleophilic substitution reactions do not take place easily with aromatic systems, right? So why? Because of course the bond is so strong, it cannot be removed easily. Because of resonance, there is always a partial double bond character, right? And hence you cannot use it directly. So we'll learn about this thing, also, that what I mentioned is, if you have got like this, and sorry, if you have got यहाँ पे say OH, right, phenol, if and I'm treating with HBr, then no reaction. So that means your SN reaction is not working here. It is not working here, right? So we'll learn about it. Let's try out few questions quickly. So when see in the first part, you have to write the formula of the corresponding alkyl halides that you can obtain from these reactions. So just think about it. I'll give you all 1 minute about it. Okay, so you see that you are dealing with NaBr and you are having H2SO4 also. So what is going to happen, right? So in presence of this, OH should be replaced and you will obtain Br over here, right? Simply substitution reaction. In second one, there is a tertiary alcohol. So concentrated HCl is there. Just at room temperature, your OH will be replaced by Cl, right? It should be replaced by Cl over here. Here you have got a secondary alcohol and you are reacting this with PbR3. So like 3 such molecules will react with this and all of them will have bromine in place of OH over here. 3 such molecules will be formed and here you are going to have H3PO3, phosphorus acid. Here you have got Pi3. Now you cannot have Pi3 directly, so you have got in situ. Remember, that is red phosphorus with iodine. So again Pi3 is formed. So again in like the C case, this will replace OH and I will be attached over here. So the answers should be somewhere like this. The first one can see very well now, right? Second one, see in B, OH is replaced by Cl now. In C, again this OH is replaced by Br, and in D, your OH is again replaced by I. Fine. So this was all about preparation of alkyl halides from alcohols. So in next class, we'll take this story further and discuss preparation of alkyl halides and aryl halides in further with the help of different class of compounds. So alcohols we have discussed. So I hope you have enjoyed attending the session. Any doubts you have got your segment where you can upload your queries, your questions. Please do so. And here's your mentor Rahul Ghosh taking leave for the time being. See you in the next class. Bye. Take care.